So the thing is, what are the deterrent 4 necessary conditions for a deadlock? The 4 necessary conditions, the first one you already know, that mutual, you can say, exclusion condition. Mutual exclusion. So what do you mean by actually mutual exclusion? That you already covered, that a resource may be acquired exclusively by only one process at a time. মানে একটা রিসোর্স একটা সময়ে একটা প্রসেসই যেন সেটাকে হোল্ড থাকতে, তার মানে the main condition is that may be acquired exclusively by only one process, only one process at a time. That you can say about mutual exclusions. The second one, the conditions, that is, you can say, hold and wait conditions. Second condition is hold and wait. So now what do you mean by hold or wait? Or you can say wait for conditions is also the same thing. So a process that has acquired an exclusive resource that may hold that resource while the other process waits to obtain other resources. তার মানে একটা প্রসেস সে কি করবে, একটা রিসোর্সকে ধরে রাখবে কখন, যখন অন্য প্রসেস ওয়েট করবে আদার রিসোর্সেসের জন্য, মানে হোল্ড করব এবং ওয়েট করব আদার, যতক্ষণ না প্রসেস আমি পাই। মানে আমি ধরো একটা প্রিন্টার আর স্ক্যানার নিয়ে কাজ করছি, আমি প্রিন্টারটাকে ধরে আছি এবং স্ক্যানারটা যতক্ষণ না আসছে ততক্ষণ আমার প্রসেসটা কমপ্লিট হচ্ছে না। তার মানে আমি প্রিন্টারটাকে ধরে স্ক্যানারটা যতক্ষণ না পাচ্ছি ততক্ষণ আমি ওয়েট করবো, কারণ আমার প্রিন্টার অ্যান্ড স্ক্যানার দুটোই লাগছে। That's why hold and then we should wait. That means you can say a process that has acquired an exclusive resource that may hold that resource while waits to obtain other resources. The third thing is that non-permission condition, and you already that non-permission conditions. That means once a process has obtained a resource, the system cannot remove it from process control যতক্ষণ না পর্যন্ত প্রসেসটা ফিনিশ করে রিসোর্সটাকে। তার মানে আমি প্রিন্টারে 10টা পৃষ্ঠা প্রিন্ট করতে দিয়েছি, আমার ফট করে 5টা পৃষ্ঠা প্রিন্ট হলো, আমি সেখান থেকে প্রসেসটাকে বাদ করে অন্য একটা প্রসেসকে চান্স দিলাম, এরকম হবে না। যতক্ষণ না পর্যন্ত ওই যে প্রিন্টার রিসোর্সটাকে ইউজ করছি, 10টা পৃষ্ঠা প্রিন্ট করতে দিয়েছি, যতক্ষণ না 10টা প্রিন্ট কমপ্লিট হচ্ছে ততক্ষণ অন্য প্রসেসকে সেটা দেওয়া যাবে না। তাই জন্যই বলছে নন প্রিমশন মানে হচ্ছে once process has obtained a resource, the system that can remove it from the processes control. From the processes, the process has finished using the resource. Finished using resource. And the last one, that is called the condition of circular wait, that would be asked in different interview. deadlock. So circular is also same. That means two or more process that are locked in a circular chain in which each process is waiting for one or more process that the next process in the chair is holding. That means I am saying that this is a P1 is a process that is waiting for some resources R1. That resources is some process P2. P2 is acquired a resources something say, and P1 is also waiting for. So what I am saying that P1 is a process which is holding a resource R1 that is required by the process P2, and P2 is holding a resource R2 that is required by a process P1 to complete its execution. That মানে P1 R1 কে ধরে রেখেছে R2 এর জন্য ওয়েট করছে, P2 R1 R2 কে ধরে রেখেছে R1 এর জন্য ওয়েট করছে। দ্যাট মিন্স একটা সার্কুলার ওয়েটে আমি এইভাবে রিপ্রেজেন্টেশন দিলাম, তুমি অন্যভাবেও ধরতে পারো যে P1 is waiting for resource R1. This R1 resource is particularly held by, আমি এভাবে লিখে দিতে পারি, held by process P2, and P2 is acquiring a resources R2, and R2 টা আবার P1 এর ওয়েট করছে R2 এর জন্য। দ্যাট মিন্স এটা সার্কুলার ওয়েট হচ্ছে। তার মানে আমি বলতে পারি that two or more processes, two or more processes are locked, you can say, in a circular chain in which you can say each process is waiting for is wait one or more resources, one or more resources that next process. So next process in holding, that is called the circular wait. These are the necessary conditions. That means the existence of a deadlock that implies that each of them must be in effect. So these four conditions are necessary and sufficient for deadlock to exist. মানে if they all are in place the system is deadlock, মানে এই চারটেই যদি অকার করে, মানে মিউচুয়াল এক্সক্লুশন হলো না, হোল্ডেন ওয়েট হলো না, প্রিমসন হলো, সার্কুলার ওয়েট কন্ডিশনস হলো, then you can say that deadlock will occur. তো আমাদের কি লাগে ডেডলকের তালে অকার করলে, then we need that there are four areas of interest in deadlock research. If we consider about the deadlock, then there are four areas. The first area is deadlock prevention. First is deadlock prevention. The second you can say that deadlock avoidance, that is deadlock avoidance. The third one you can say deadlock detection, and the fourth one you can say deadlock recovery. So our chapter is organized as follows. First is deadlock prevention. This is not first I am discussing, I will start discussions with deadlock detections. So what is deadlock prevention? You can say that our concern is to condition a system to remove any possibility of deadlock occurring. মানে প্রিভেন্ট করছি, মানে প্রিভেনশন ইজ এ ইউ ক্যান সে অ্যাবাউট এ ক্লিন সলিউশন অ্যাজ ফার অ্যাজ ডেডলক ইটসেলফ ইজ কনসার্ন। বাট প্রিভেনশন মেথডের অসুবিধা কি, ক্যান অফেন রেজাল্ট পুয়ার রিসোর্স ইউটিলাইজেশন, কারণ আমরা প্রথমেই তো প্রিভেন্ট করার চেষ্টা করছি, তারপরে রিসোর্স ইউটিলাইজেশন যেটা হচ্ছে সেটা অত ভালো এক্ষেত্রে হয় না। So you can say that deadlock prevention, you can say, is to, you can say, condition a system to remove any possibility, any possibility of deadlock occurring. So you can say, but that will create a problem. What? That result in poor resource utilization. Poor resource utilization. Now the question is deadlock avoidance. So the goal is to impose less stringent conditions that in deadlock prevention. Deadlock prevention এর চেয়ে একটু less stringent conditions apply করি যাতে better resource utilization করা যায়। Avoidance মানে do not precondition that the system to remove all possibility of deadlock. আমি avoidance মানে কি অ্যাভয়েড করার চেষ্টা করছি, প্রিভেনশন মানে ডেডলক হবে না তাই জন্য পুয়ার রিসোর্স ইউটিলাইজেশন হয়। বাট অ্যাভয়েডেন্স মানে কিন্তু আমি গ্যারেন্টি দিচ্ছি না যে আমার ডেডলক হবে না। আমি কি করছি, আমি চেষ্টা করছি যে কিছুটা অনেক পসিবিলিটি অফ ডেডলকগুলো যাতে না অকার করে। মানে দে অ্যালাউ করছে পসিবিলিটি টু লুম, বাট হোয়েন এভার এ ডেডলক ইজ অ্যাপ্রোচ ইট ইজ কেয়ারফুলি সাইড স্টেপস। সো ইট ইজ অ্যাকচুয়ালি দ্য গোল ইজ টু, you can say, goal is to impose, that is impose less stringent conditions, less stringent conditions in deadlock prevention in an attempt to get better resource utilization, better resource utilization. সো অ্যাভয়েডেন্স মাথায় ঢুকিয়ে নাও যে এটা মানে কিন্তু এরকম আমি দেখছি না যে সমস্ত পসিবিলিটি অফ ডেডলককে অ্যাভয়েড করছে, বাট ইনস্টেড ও কী করছে, যখন একটা ডেডলক অ্যাপ্রোচড হবে তখন ও কেয়ারফুলি যেন হ্যান্ডেল করতে পারে। অ্যান্ড দেয়ার ইজ এ ডেডলক ডিটেকশন। সো এটা মানে কি, ডেডলক ডিটেকশন মানে ডেডলক অকার করেছে কি করেনি সেটা চেক করা। So it is used to clear deadlock from a system. Deadlock, you can say, which deadlock can occur or not. So that methods are used in system deadlock can occur. আমি চেক করে নিই, তাই জন্য যে সিস্টেমে ডেডলক অকার করার একটা সম্ভাবনা আছে সেই সিস্টেমে আমি কি করি, ডেডলক ডিটেকশনসটা করি। মানে গোলটা কি, এর গোল হচ্ছে is to determine, is determine if a deadlock has occurred or not. ডেডলকটা অকার করেছে কি করেনি সেটাই ডেডলক ডিটেকশনে চেক করে। অ্যান্ড ডেডলক রিকভারি কি, দ্যাট অ্যাকচুয়ালি ডেডলক অকার করে সেটাকে রিকভার করা হয়, দ্যাট আর ইউজড টু ক্লিয়ার deadlocks from a system so that it may operate freedom, it may operate freedom, and so the process actually may complete their execution, complete their execution and free their resources and free their resources. So that is the fourth case. So we are starting discussion from the third number conditions, which is called that deadlock detections. তার মানে আমি ডেডলকটাকে ডিটেক্ট করব কি করে, that is the thing. So first is deadlock detection. So in case of deadlock detection, so you know that this is the process of determining that a deadlock exists, and you have to identify the processes and resources involved in the deadlock. তার মানে ডেডলক ডিটেকশন অ্যালগরিদম জেনারেলি ফোকাস হচ্ছে অন ডিটারমাইন ইফ এ সার্কুলার ওয়েট এক্সিস্ট করে কি করে না, given that the other necessary condition for deadlock are in place. মানে আমরা ধরে নেওয়া হয় সাধারণত other deadlock conditions already আছে, এবং আমরা সাধারণত এই মেথডের মাধ্যমে চেক করি যে সার্কুলার ওয়েটটা এক্সিস্ট করছে কি করছে না। সো দ্য ফার্স্ট থিং যেটা আমরা ডেডলক ডিটেকশনে ইউজ করি, দ্যাট ইজ কল রিসোর্স অ্যালোকেশন গ্রাফ, you can say resource allocation. That is the thing that we wait to detect the deadlock. So what is resource allocation graph? So there are some conditions you should know, that say a process is by say P1, and this process is requesting, we are giving a circle, we are denoting the you can say the resources, and the arrow actually from P1, that actually if we write it precisely, it will touch actually the proximity extremity of the large circle, that indicate that the resource request is under considerations. And so you just look carefully that the process P1 is actually, you can say, it touches the extremity of the circle, which is resource R1, and within this if we write two circles, that means what I am saying, that P1 is, you can say, testing a resource of, you can say, type R1, of which there are identical resources. What does it mean? R1 is printer, আমার কাছে দুটো প্রিন্টার আছে, তাই জন্য আমি দুটো সার্কেল ভেতরে করেছি। মানে P1 হচ্ছে একটা প্রসেস যে কি করছে, প্রিন্টারটা চাইছে, একটা প্রিন্টারই চাইছে হয়তো, তখন আমি কি করছি, একটা প্রিন্টার দিয়ে দিলাম। অ্যাকচুয়ালি আমার কাছে দুটো প্রিন্টার অ্যাভেলেবেল আছে, সেটা বোঝানোর জন্য আমি এইভাবে লিখি। Or it may be that particular resource, say that is R2, it has two instances, দুটো প্রিন্টার আছে, that is already been allocated to process P2, then that should be written like that. That should be written like that. What does it mean? That we can say one of the two identical resources of type R2 has been allocated to process P2. So that means, or you can say that, say process, some process, say name of the process is P3, that process is actually requesting a resources R3, and that particular resource, only one instance is available, that particular resource, that should be the proximity. uh, so you can say that will be touching like that, and that particular resource is already been allocated to P4. It may happen. You can say it already can be, you can write like that, that say process P5 is there. This is a process P5. That process P5 has been allocated resource R5. Say this is the resource R5. It has only one instance. That particular resources, you can say that process P5 has been allocated that resources R5, that has been requested by process P6, that has been requested by process P6, that has been allocated resource R4. This, that has been allocated R4, that is being requested by process P5. So that is the classic example of circular. Wait, just hold a minute, just hold a minute. So the thing is that this is the one of the example. You can say that this is the classic example, you can say, about classical circular weight. And if a circle exists, then you can say that there is a possibility to appear deadlock. That means the if in resource allocation graph there is no cycle, then deadlock not present, and if in resource allocation graph there is a cycle, then deadlock may or may not present. So what is the actual deductions that we get from that? In in resource allocation graph there is, then we can say deadlock not present, that deadlock not present. And if in this resource allocation graph there is a cycle, then deadlock may or may not present. You can say about that. That is the utility of using resource allocation graph. So you can say that if the resource allocation graph is like that, say you can say particular resource and R2 is another, say, resource is like that, and they will give some conditions, and depending on that you can just draw the graph. It may be possible that the graph should be like that, that means the thing, it may be like that. I am just writing it approximately, that may be possible that it would be like that. If there is a cycle is present, say P3 is another process, if a cycle is present, then you will say that that can cause a deadlock. So the thing is that that is the one of the example of resource allocation graph. And the thing is, uh, you can say that if a process resource request that may be granted, then we say that the graph may be reduced by that process. That means ধরো একটা করে প্রসেস এক্সিকিউশন কমপ্লিট হচ্ছে এবং একটা করে আমি রিসোর্সটাকে ছেড়ে দিচ্ছি, এবং সেখান থেকে যদি ছাড়তে ছাড়তে আমরা দেখি যে একটা সিস্টেম পেলাম যেখানে দেখলাম যে কোনো সাইকেল নেই, তাহলে উই ক্যান সে দ্যাট ডেডলক দেয়ার ইজ এ গ্রাফ রিডিউস করে যে নো ডেডলক এক্সিস্ট করে। কিরকম ভাবে বলছি, ধরো আমি একটা জাস্ট একটা জেনারেল এক্সাম্পলস দিচ্ছি দ্যাট সে এরকম একটা সিস্টেম অলরেডি বিন ইজ গিভেন। তুমি ধরো এরকম দ্যাট সে দিস ইজ এ পি এরকম হবে, that is also P8, say that is taken by that, say this is R7, say there are three processes, and say that is being taken by, and there are another process P9 that would be taken by that, and that particular resources is taken by this P7. So that's one type of graph that is requesting this. So actually, how can we say that by using graph reductions that no deadlock exists? It may be given that say that P9 is executing. P9 completes its executions. So if it completes its executions, then we can reduce the P9. And the thing is that the graph should be like that, that you can say if we just reduce it, that means we just remove the P9, that means the thing is that P7 is there, that is complete P8, that is corresponding R7, and this is the actual the thing that is given. You can say there are three resources, there are two resources, you can say that P7 is executing like that, that is be taken like that, that is taken like that, and this is requesting this. So if line is executing its completes executions, then it just relinquishes his resources, তার মানে এই রিসোর্সটা ফাঁকা হয়ে গেল, and then you can say that it completes its executions. If P7 completes its execution, then what we can do, we can remove this particular arrow, and we can remove this particular arrow. So P7, you can say that also that particular arrow can also be reduced. uh, so P7 is executing, its executions completes, and after that if you say that P8 is completes its executions, then you will find that we will get the graph like that. So if we get the graph like that, so you can say mm, this is removed and this is removed, and you can say that it would be like that. So by graph reducing that, we can see that there are no deadlock exist if the operations would be like that. So by resource allocations graph, we can also by using the graph reductions, and we will find that no deadlock will exist. So that is the one of the procedure. But the thing is that there is another type of thing you can do that actually comes in your like that in transactions examinations, in because in that particular database there is also a deadlock, but there is a graph you can say, mm, that is a wait for graph. Actually that will be actually discussed in your database, but I am discussing here because it's a one several same type of problems are there, that is called you can say wait for graph. That means that just similar conditions are there. That means if there is a circle, then you can say that there is a deadlock. If there is no circle, that there is maybe possibility of deadlock, or may not deadlock will occur. But the thing is that that type of graph, like that, in this graph is known as resource allocation graph, but this type of graph is known as, you can say, uh, wait for graph. I am just giving an examples to show you what do you mean by that. You can say that is the example of wait for. Actually that will be in transactions in database chapter, but I am discussing here because some examples are same as that, so that the transactions are like that, and item locked by transactions is given, and as well as data items uh, transaction is waiting for, data items and transaction waiting for. So that is the thing, you can say. So transaction is T1, that is T2, that is T3, T4, that is T5, that is T6, that is T7. And, that is locked by the transaction, say x2, that is given, x3, x10, that is x8, that is x7, that is x1, x5, I think that is x1, x4, x6, and that are waiting for, that is x1, x3, x7, x8, uh, x4, x5, say x1, x3, this is x6, this is x5. Now what will happen, you have to draw the graph. So say you can say, if we draw the graph, say this is the transactions, particular item locked, you can say this transactions T1 locked item x2, and he is waiting for x1 and x3. It is waiting for x1 and x3. So you can say what will happen, and this particular x1, this particular x1 is locked by T5, and this particular x3 which is locked by T2. Then the graph should be like that. This is a T2 transaction, and that particular transaction is, so we are giving like that. This is x1 and this is x3. You just clear about T1 is a transactions that is locked by this locked x2 is locked by T1, and T1 is waiting for x1 and x3. X1 is locked by transactions T5, and x3 is, so that means we are giving arrow like that, the T1 to T2 and T1 to T5. Similarly, like that, you can see that transactions T2, he is locking x3 and x10, and he is waiting. I am just saying about waiting x7 and x3. Now x7 is already been taken by T4, x by T3. So from transactions T2, what we can say, that this is a T3, and the arrow should be like x8, because x8 is be taken by T3, and x7, that is the transactions T4, and if we like the transaction T4 is like that, then that particular x7 transactions T4. You have to look all the stuff, like the transaction 3 3, it is waiting for x4 and x5, and x4 is taken by t6 and x5 is taken by t5. You say that if this is a t3, then you can say t3 is x4, so x4 is taken by t6, so t2 to t6, say this is a t6, we are writing x4, and x5, x5 is already been occupied by t5, so you can say t5 is there, so I am just giving an arrow from t3 arrow, and we are writing the corresponding x5. So you have to draw all the graphs, because that is t4. Now we are coming to t4. T4 is x1 is already been locked by, so arrow from t4 to t6. So you can say if we give an arrow from t4 to t6 like that, so it should be like that, t4 to t6, this is x1. So you have to draw like that, and you will find that if there is a cycle, then you can say it can create a deadlock, that my deadlock হবে. So the thing is that that is the one of the example of wait for graph. So whether the deadlock arises or not, since we are actually getting a graph, and there in a graph there is a cycle, then we can say that of course the deadlock may occur. So this is the two deadlock, you can say, deadlock detections by using resource allocation graph, and as well as in transactions there is a wait for graph, and so we are dealing with that. Now the thing is that the next thing we can say that deadlock, you can say deadlock avoidance, where uh, the main thing of deadlock avoidance, there is an algorithm that will come in your different competitive exam. The next thing is, you can say, deadlock avoidance, you can say deadlock avoidance. So in case of deadlock avoidance, mm, we know that it prevents deadlock by restraining how request can be made. Restraining means আমরা একটা restrictions দিচ্ছি যে কিভাবে বা একটা প্রসেস বলছি যার মাধ্যমে you can avoid the deadlock. So restrain যেটা হয়, that ensure that at least one of the necessary condition for deadlock cannot occur, and that deadlock cannot hold, তার মানে একটা particular conditions occur করতে দেওয়া হবে না, that is a deadlock avoidance বলতে আমরা বুঝি। তো এখানে দুটো রকম, you can say that deadlock avoidance এর famous যেটা Dijkstra's Banker's algorithm, that famous, you can say, algorithm, that is a Dijkstra Banker's algo, and because the strategy is modeled after a banker who makes loans from a pool of capital and receives payment that are returned to the pool. So that's why bankers একটা লোন নিয়েছিল এবং সেইটা কিভাবে শোধ করেছিল, এবং সেইটাকেই আমরা অ্যাকচুয়ালি ফ্রেজ করে এই ডাক্সটা ব্যাংকার্স অ্যালগরিদম হয়। So this particular algorithm, that actually, you can say, defines how a particular, you can say, system can, you can say, prevent deadlock by carefully controlling how resources are distributed, how resources are distributed to. So ব্যাংকার্স অ্যালগরিদম জানার আগে আমায় দুটো জিনিস আমি জানবো যে উম, একটা সেফ স্টেট বলে যে there is a thing which is called safe state. So what do you mean by safe state? If we say if the operating system can guarantee that current process, all current process can complete their their work within a finite time, then we can say that is a safe state. If not, then the system is said to be in an unsafe state. Of safety and unsafe state, I am explaining it by using some examples. That will be the better thing to understand what do you mean by safe and what do you mean by unsafe state. The thing is that, and say you can say example of safe state. If we say, so we are just discussing, there is a process, say p1, p2, that that you can say maximum need. So a maximum number of resources actually that the process requires during its executions, so that is the maximum need. And so it has been given the 8. A currently given loan, you can say about loan, this is a process pi. Pi means any process, that is you can say current loan, that means already been given. One resources is given to process p1, four resources are given to process p2, five resources are given to process p3, and that is the claim. That means they needed claim, and say that is 3 to 3. So actually you can say that total resources say is 12, and available resources say is 2, because you can 5, 4, 9 and 10, total is 12 resources are there, and already been in current you can see that 10 resources are given, so only available resources are 2. Now in that case this state is safe. Why? Because it is possible for all three processes to finish. Note that you can say that process p2, that process p2 is currently has a loan of 4 processes, currently has a loan, and will eventually need a maximum of 6, we know that. So 2 additional resources are now its claim. So since the available resources are 2, so you can give process p2 to these 2 resources such that p2 can finish, and after p2 can finish it can release. This is the 4 which is current loan, and you are given 2 resources, so when the p2 is finishes it releases 6 resources, it releases 6 resources, and by using these 6 resources you can execute p1 and p3 in any order. Either you can execute p1 then p3, or either you can execute it p3 p1. So that is the safe state. Why? Because safe, because it is possible for all three processes to finish. So the now if we say what should be the example of unsafe state. You can say, if we say what is the example of unsafe, in case of unsafe state, so you can say there is a process say that maximum need is say 10, 5, 3, say current loan, that is 8, that is 2, that is 1, and say current claim, that is 2, that is 3, 2, and total resource that is available, that is 12, and available resource is only 1. What you can say that uh, what we can say that if this particular, there are 12 resources, so if we sum the value of third column and subtract from 12, only one resources are available, that is the corresponding available. Now at that point, no matter which the available resource, we cannot guarantee that all the three processes will finish, because P1 will take 2, need 2, P2 will need 3, and P3 need 2. If we give one resources to P3, then the P3 will not complete and it cannot relinquish all the resources. So that means that it may be supposed that process P1 request and it granted, so last available resources. So a three-way deadlock could occur if indeed each process needs to request at least one more resources, because after getting one resources there is no available resources and P1 is not completed its resources, so P1 is waiting for resources, P2 is also waiting for resources, P3 is also waiting for resources. So it is creating this answer state, of course create a deadlock. But the thing is that you should remember that it is important to note that unsafe, that imply the existence of deadlock, nor even that deadlock eventually occur. So when an unsafe state does not imply that it will lead to a deadlock, there is a possibility to occur in deadlock, but unsafe state মানেই যে deadlock সেটা কিন্তু নয়। unsafe state মানে there is a possibility to occur deadlock, বা deadlock occur করতেও পারে বা deadlock occur নাও করতে পারে। সো দ্য থিং ইজ, আমরা এটা যাওয়ার আগে আমরা একটু ব্যাংকস অ্যালগরিদমের যেটা তোমাদের পরীক্ষায় আসে সেটা নিয়ে একটুখানি দেখে নিতে হবে, যে আমরা কিছু জিনিস এখানে বার করি প্রথমে, সেটা আগে বোঝো, দেন আমরা অ্যালগরিদমটায় যাব। তার মানে আমার যেন এটা ক্লিয়ার হয় আনসেফ অ্যান্ড সেফ স্টেট মানে কি, এবং আনসেফ মানেই কি ডেডলক হবে সেটা কিন্তু গ্যারেন্টিড নয়, আনসেফ মানে ডেডলক হওয়ার প্রবাবিলিটি আছে, আবার সেফ স্টেট থেকেও আনসেফ স্টেটে চলে যেতে পারে, দ্যাট ইজ অলসো, মানে এখন সেফ স্টেট আছে হঠাৎ করে রিকোয়েস্ট এমন এলো যে উই আর গেটিং আনসেফ স্টেট। সো দ্য থিং ইজ দ্যাট আমাদের একটা স্মল অ্যালগরিদম, you can say resource request algorithms, and in case of resource request algorithm, what is this, that we can say if this request I, that means I processes, less than need, that means the request যেটা করেছি তার ভ্যালু যদি need যেটা দরকার তার তুলনায় কম হয়, then we can say go to step 2, raise error. Step number 2, if this request, what I am requesting, that is less than equals to available, then go to step 3, wait until available. And what is available? Available I is equals to available I, this need I is equals to need I minus request I, that is calculating for each process, that's why the I suffixes are there. So the allocations is, you can say, allocations plus request. So what I am saying that, uh, say if we say that process P, you can say process P is the resources, and this process P0 is, this is the need, process P0 is requesting that particular resources. So what is the and available, and there are say 756. So if we requesting this, that means this requesting is need, we are requesting 330, and that is the less than need. Of course need is 55543. So we are going to step 3 and again check what I am requesting and what is available. Available is 756. So that request is less than available, so this particular condition is true. So available minus request, so we are subtracting this, this is 2, this is 4, so this is new, you can say, available, the first step. Now need equals to need minus request, so you can say that initially the need is 543 and we are requesting 330. So now the need is 312, that is the new need. So that has been, and allocations is equals to allocations. So say initially, say allocation is there 785, say this is for resources ABC. So now the request is being permitted, that is 330. So this is now the allocation. So that is a simple thing because it will be helpful to understand the Banks algorithm. So that's why I'm just writing this. So that will be acting like that. So the first thing is that we can write the Banks algorithm. Then we will take an examples and solve it. Then how the Banks algorithm is being solved. So you can say, if we write it. So the first thing is, we can say that uh, that say work and this finish, that actually two means one dimensional matrix, you can say, and of vector of size, column vectors of size m and say n. That means finish will tell you that whether the all the process it completes its work or not, and work is a calculations. And so initially we can say this particular work with available, what is the available, and finish I, that is an vector with false. everything is now false. Whenever each and everything is true, each and every process is being completed, we are making it true by. So the thing that all the process, so I equals to 1 to n, what will happen that we have to find an I such that you can say that both that finish, that means first everything is false. If it is false, then we will do that, and we are checking that need is less than equals to work or not, because initially the work will be filled with available. Actually need will be checked that whether need is less than available or not. So if this no such I exists, that means all had been completed, and then otherwise what we have to work, we have to work what means actually available, that should be added with the allocations. What I am saying that you just see that that available should be used available plus allocations. You just see that allocations is allocation plus request. In that particular case also is with the available, and the thing is that we are dealing with that. That means if the allocation is done, then work is added with this particular allocations, and we have to make this finish two, and again go to step 2. Now if finish, now if this finish I, then the system is in safe state, system is in safe state. So you can say that with the, so I am going through process by process, the how the it will be uh, by giving an example. Say first take an example where you just forget about that, then you will be under, it will be understandable that say m, that is nothing but the number. Our example is the number of resources, and say 4 resources are available, one a b c d, and say n is the number of processes. Say there are p0, p1, p2, p3, p4, 5 processes are there, and work is initially, that is number of resources, that means 4 0 1 2 3, and initially that particular finish is number of processes, so there is 5 processes, 0 1 2 3 4, there are 5 processes, and each are initialized with false, each are initialized with false. So that is the first thing, finish is false. So now it has been given that in your exam also it should be like that, that there are maximum, there are available, and say a b c d, this is also the resources a b c d, a b c d, available is given 1520, say maximum 0012, there are 2356 0652 0656, and this is 0012 00 about 42 and 0014, and the processor p0, this is say P1, this is P2, this is P3, P4. So the first thing, they will ask you the questions that calculate you have to matrix need. So the question can be like that: calculate that matrix need matrix. You have to calculate that. Then the question schemes like that: is the system is in safe state? It may be the questions they can ask. Say if P1 0320, can it be guaranteed immediately? Can it be granted immediately? That type of questions can come. So we will discussing that thing. So the thing is that, so now that is the thing. So here you know that n is the number, that m is the resources, and this we know previously that available is a vector of size m. Allocations, this is a matrix of size m cross n, or n cross m, it is n cross m. And this maximum is also, you can treat it as a matrix n from a number of process and number of resources, and need, that is also n cross m, and that can be find by maximum minus allocation. Then we will get the need matrix. So if we find the need matrix from particular problem, for that particular problem, this is a b c d, and since this is p0 p1, this is p2 p3 p4, maximum minus allocations, that is the maximum, this is the maximum, and allocations, that is the available thing is given. So if we want to allocate this one, say আমরা allocate করতে চাই this 0012, if the request comes like that 0012, মানে process p0 কে যদি আমি allocate করতে চাই, then we will find that 0012 কে যদি process p0 কে যদি করতে চাই, তাহলে process p0 0012 request for process p0, then আমার need মানে কি maximum, that is also been needed 0012, and you have to subtract with the corresponding allocation 001. You can find that means this is the maximum and this is the corresponding allocation. So if we subtract it, then for p0 that is 1000, if we subtract this, then 0 0. For process p2, this is the maximum 2356 and the allocation is 1354. If you subtract this, then 1002. For p3 0652, and this is comes out 0020, 0656 and 0014. If you subtract it, then 2, and of course the available, that is 1520. So that is the need matrix, that is the first task we have to calculate. Now you have to see that whether if p0 completed, now you just see that this is the need, that means p0 need nothing, p0 need nothing, that means automatically p0 completed, that means p0 automatically completed. But what will happen, that after completion of the p0, p0 is completed first, and after completion of p0, p0 is allocating 0012, that means it releases that particular resources. After completion of p0, p0 will release this particular resource, that is 0012, 1 2. That means what will happen, you can say that in our vector initially ABCD that is available, that is 1520. Now after completion of P0 releases 0012. So now 152 is available, and in its vector I am doing that, since this is an vector, this is 0, this is 1, that is 0 process, P0 process, this is P1 process, this is P2. All are has been completed. Now the thing is that this is the available resources, and P1 will need this one 0750, but since that B resources P1 7, but only available B resources is 5, that means P1 is not executed at that particular moment, but P2 can execute because P2 only need 1002 and that is available 1532. That means we can say after P0 P2 can execute. If P2 can execute, so after the execution P2 hold, that is what it holds, that means it will hold 1354. It will hold 1354. You just see in the previous that allocation is 1354, that is the allocations. And so after execution of 1002, because available is 1532, so P2 completes this execution and it releases 1354. So it releases 1354. So if it releases 1354, then what you can say, that number of resources, that is 6, 8, this is 8, this is 2, that is now available. So now since this is available, now you can execute either P3 or you can execute either P1 because this is now available. So if we execute P1, then taken this and P1 completes its executions, that means that is P2 become true, is execution, so it becomes. And since we know P releases its resources, what the resources they help P1 allocation is 1000. So P1 allocation is, you can say, 1000. So you can say that it completes its execution. What is the P1 that allocated? P1 is complete. If P1 is complete its allocations, then you can say it releases 1000. So 1000. So now the work is 3886. Now P1 is executed. Now you can give P3 chances because anything can execute it. So P3 will be executed, and if P3 will be executed, then you will find that P3 will release 0632. So P3 will release 0632. This is 11, this is 14, this is 3. Then you can execute everything is true. Then after true, you can say that is one of the sequence of the safe state. This P0, P2, P1, P3, P4. So that is the procedure by which you can say that that is the one of the procedure of Banker's algorithm, where you can say whether the safe state exists or not. If safe state exists, then there is no possibility of deadline like that. So the thing is that we will solve several math, but the thing is that there is another thing you can say that we are covering the deadlock detections as well as the deadlock avoidance. Now there are two things, but there is no problem such exist. One is you can say the deadlock recovery, and one is you can say that deadlock uh, prevention is one of the things. So if we talk about the step that is deadlock prevention, if we talk about the deadlock prevention, that we know that for deadlock to occur, each of the four necessary conditions must be held. So by ensuring that at least one of these conditions cannot hold, we can prevent the occurrence of a deadlock. That is the main thing about deadlock prevention, that we know for a deadlock to occur, we know each of the four necessary must. So by ensuring at least one of the conditions cannot hold, one of the conditions cannot hold, we can we can prevent the occurrence of a deadlock. We can prevent the occurrence of a deadlock. That is the thing. We know the four conditions: mutual exclusions, hold and wait, no preemptions, and the corresponding is circular wait. If we ensure that one of the conditions cannot hold, so we can guarantee that deadlock can be prevented. But that is a difficult thing. And one thing, that is the last thing about deadlock, that is called the deadlock recovery. That means you can say that recovery for from deadlock, or you can say deadlock recovery. That is the fourth module, that is called deadlock recovery. And you just know that when a deadlock algorithms that determines that a deadlock exists, several alternatives are available. One possibility is to inform the operator that a deadlock has occurred, to let the operator deal with the deadlock manually. Another possibility কি হতে পারে, let the system recover from the deadlock automatically. There are two options for breaking a deadlock. One is simply abort করে দাও one or more process to break the circular wait, and the other is to preempt some resources from one or more of the deadlock process. So that we can actually do in deadlock recovery. One, you can say we can just process terminations. We can say process termination is one of the process. So process termination means যে যেগুলোর জন্য abort abort করে দিলাম, we all deadlocked, abort all process. We can say abort one process, about one process at a time until the deadlock cycle is eliminated. So that is a simple thing that you already do. Process termination, we are just eliminating the deadlock by aborting the process. We use one or two methods. In both methods, the system reclaims all resource. That means abort all deadlock process, or you can say abort one process at a time until the deadlock cycle is eliminated. And another thing, that is resource preemption. That is the process preempts terminations, and another is resource preemption. And resource preemption, that means that we have to eliminate deadlock using the resource preemption. That means we are successively preempted some resources from process, and we are give these resources to other processes until the deadlock cycle is broken. So that is the case. There are two cases also. That means first is we are selecting a victim. What does it mean? That means when a resources and which process are to be preempt, আমাকে কোন প্রসেসটাকে প্রিম্ট করতে হবে, বিকজ প্রসেস টার্মিনেশনে আমরা কি দেখলাম, উই মাস্ট ডিটারমাইন দ্য অর্ডার অফ প্রিমশন টু মিনিমাইজ কস্ট। সো কোন প্রসেসটাকে আমায় অ্যাকচুয়ালি কোন রিসোর্সটাকে প্রিমশন করতে হবে, দ্যাট ইজ কল্ড দ্য সিলেক্টিং এ ভিকটিম, মানে যার জন্য গন্ডগোল সেইটাকে প্রথমে সিলেক্ট করতে হবে। অ্যান্ড দেন দ্য থিং ইজ রোল ব্যাক। আমরা রোল ব্যাক পড়েছি। রোল ব্যাক means if we preempted a resource from a process, what should be done with that process? So it cannot clearly continue with its normal execution, তার মানে ওকে আবার রোল ব্যাক করে প্রসেসটাকে আবার সেফ স্টেটে ফিরে যেতে হবে এবং রিস্টার্ট করতে হবে, দ্যাট ইজ কল্ড রোল ব্যাক। অ্যান্ড দ্য থিং ইজ দ্যাট থার্ড থিং ইজ দ্যাট starvation. And so how do you ensure that starvation will not occur? Of course you have to ensure that starvation will not occur. So that is, how can we guarantee that resources will not always be preempted from the same process? মানে রিসোর্স যেটা প্রিম্ট করছি একই প্রসেসটাকে যেন বারবার সব কিছু প্রিম্পটেড না হয়। সো ফার্স্ট সিস্টেম ওয়্যার দ্য ভিকটিম সিলেকশন ইজ বেস্ট হয়, প্রথমে ভিকটিমটাকে সিলেক্ট করা হয় অন দ্য কস্ট ফ্যাক্টর, যেখানে আমার কস্ট কম, কস্ট মানে টাকা নয়, এখানে কস্ট মানে টাইম বা কনজিউমিং বা এইসব ফ্যাক্টর রিপ্রেজেন্ট করছে। ইট মে হ্যাপেন দ্যাট সেম প্রসেস ইজ অলওয়েজ পিকড অ্যাজ এ ভিকটিম, সেটা যেন না হয়, তার মানে দিস প্রসেস নেভার কমপ্লিটস ইটস ডেজিগনেটেড টাস্ক, so that means starvation situations that can come. So that's why you have to careful to select a victim for which the actually the resource should be preempted. So that is the total, you can say, the deadlock chapters, and from deadlock chapter I am just sending you some problems, you can solve it and uh, uh, just see that whether it can be possible for you to solve the problems or not. So I think